Hi everyone, thanks for attending this talk. I think everyone is having a good day. Our talk is a tale of making internet pollution free, finding and exploiting client-side prototype pollution in the wild. So how many of you are aware of this vulnerability class? Yeah, so we will talk about prototype pollution in a while. So first of all, who are we and why you should care about this vulnerability at all? This is Harsh. I do generally web application security and I do a lot of shit posting on Twitter. My handle is RootXHarsh and Mohan, can you introduce yourself?
Yeah, this is Mohan Sriram Krishna. I like browsers, Electron, and CTF. I'm also known as Sirius on Twitter. You can find me on Twitter.
Cool. Yeah, so what's in the agenda for today? We'll start off by learning about JavaScript, the basic fundamentals of JavaScript. Because the vulnerability revolves around JavaScript, it's very specific to JavaScript. We need to understand some basic terminologies and functionalities of it. You need to be very clear about the building blocks of JavaScript before jumping right into the vulnerability itself. Then we will move ahead with the vulnerability class, that is prototype pollution. Then we will show you our methodology, what everything we use to find the vulnerability at scale. We will also show you some case studies and research result from our research. Then finally, we will move ahead with the mitigation part of the vulnerability. So yeah, let's start with JavaScript prototype. So what is JavaScript? Like, what kind of language it is, right? So it is a prototype-based language. What that means is, unlike C++ or Java, it doesn't use a classical inheritance. It uses something called an internal object called prototype. And every object you create in JavaScript basically inherits its properties and methods using this internal object called prototype. So this prototype-based inheritance is cool, but it comes with its own loopholes. And that's exactly what we will be discussing today in the later slides. So here we have a flowchart which will try to explain the difference between classical inheritance and prototypal inheritance. So in the classical inheritance, we have, for example, you want to create a class called animal, and then you want to create another class called dog or cat. And you want to have all the properties of animal class, all the properties and method of animal class within the dog or cat card. So what you will do is you will use a syntax similar to class dog extends animal. And then when you create an object of class dog, you will have access to all the properties and methods of animal class within the dog object. So that's how you do it in normal C++ or Java. But when it comes to JavaScript, things get a bit tricky, right? So for example, here we have an animal object. You define your properties and methods within it. And if you want to copy these methods and properties within dog, so what you would do is you will use a syntax like dog.prototype is equal to object.create, and you will pass animal's prototype as an argument to it. Now the blueprint or the baseline for the dog object will be that of animal. So you will have access to animal's properties within it. So that's how this two differentiate. Let's move ahead with another flowchart. So this is like a more extended flowchart on the same thing. So here we have a string, an object called A with property series, right? And it points to like the proto thing points to the constructor's prototype. So that is object.prototype in this case. Then which basically points to null. So that is the top of chain. Then we have this string called S, which points to string.prototype. And that points to object.prototype. So you see, everything basically inherits from there. This animal object also inherits from there. So everything inherits from there. If you create an array, it will also inherit from here only. So that's how the prototype chain goes on. So what we explained here, like the flowchart explains a prototype chain. So if you were to basically search for access a property within that A object, it will first try to access it within A. Otherwise, it will go to the object.prototype, and if it finds there, it will basically say this is the value of it. Otherwise, it will just return null. So that's how it works. So now that we know about prototype chain, let's see the vulnerability class itself. That is prototype pollution. Okay, so we know that every object is inheriting its properties from object.prototype. So uh, what would happen if someone can get hold of this object.prototype? What if someone can add their own property to this object.prototype? So if you are going in the direction, it will be available in all the object you create. That is right. That is exactly what will happen. Now, if you create any object or if any past object you created has access to that property. So here we have another flowchart explaining the very same thing. So for example, we have this object.prototype where we have set the property pollute with this random value, right? Now, if you go to this object A, and if you try to access the property pollute, it will search within it, but it's not there, right? It doesn't exist there. So it will go to the its constructor prototype, so that is object.prototype, and it will try to access it there. And because it exists there, it will return its value. So even though the property doesn't exist there, it will get that value from the object.prototype. So that is the concept of the vulnerability. You try to pollute that main top of the chain thing, and you will have that value in everywhere. So for example, here we have a string called s. Then we are again searching pollute property within s. It is not there. It will try to access it within string.prototype. It is not there. It will go on the top of chain. It finds it there. It returns its value. So and so on. This is how the concept of vulnerability works. Okay, so that was the concept. Now let's see an example how this vulnerability will introduce in a code base or on the client side, to be specific. So here we have code snippet. Anyone can see or read this code snippet? Or if not, I can just go over it, right? So we are basically taking all the query parameters and taking for example, if I pass user is equal to hash, we will pass the user query parameter as a property of the query object. So the returning query object will become user user, and its value will be hash. So that's how we are passing it. Okay. Yep. So what if we pass user square bracket ID square bracket is equal to 1? So here we have another check where we are checking if value, if the query parameters are passed in like k1 square bracket, k2 square bracket is equal to value, then it will, go in a, kind of recursion, and it will add that as a nested object. So now the user object becomes a nested object. It has another object which has the ID property and its value 1. So you see that's how a nested object is created using this input. So what if we pass this special property called underscore underscore proto underscore underscore. So foo is equal to bar. So you say it doesn't return it there. So where did the proto go? That's the question, right? So like we said, it points to constructor's prototype. So you try to query the query object, you get user ID 1, right? Then if you go into the hidden property called prototype, that is the internal object, you get the foo bar. Now if you create another object called new object and try to exit the foo property on new object, it is there. You see the bar is returned. So it is returned because it is at the top of chain. We have polluted the top of chain. So from now on, we will show you the methodology to find this vulnerability at scale. Mohan will take it from there.
Yeah. Now I'm going to discuss about the methodology we used in this whole research. Like you can see the flow chart here. You can find all the stuff we did during the whole research. Basically, there are mainly two important parts in the whole research. First one is detection, which is finding the prototype pollution. And second one is finding script gadgets. We'll discuss more about these two methods in the coming slides. Now let's see the detection, like what are the different stuff we did to detect a prototype pollution in bug bounty programs. So initially, we wrote a Python script, which basically takes the URLs and checks if the prototype is polluted. The basic idea is like it appends prototype pollution payload to the given URL, and if there is a vulnerable location parser, it gets polluted, right? So once it's polluted, the Python uses a Selenium bot and checks if object.prototype is polluted. If it's polluted, it will send a notification to Discord. So basically, that's how the Python Selenium script works. The thing is like you are you are spraying the payload on the given URL and praying for the pollution to occur. So the advantage of this method is like you can scale this up. You can throw millions of domains to the Python script and host the your instance on Droplet, DigitalOcean Droplet or AWS instance, and scan it for years. I mean days. It will, if it finds, it will send a notification to you. So that's advantage. But the disadvantage is like it can only find vulnerable location parsers because we are spraying the pollution and payload and hoping for pollution to occur. Like we are hoping for a vulnerable location parser. So it just sprays the payload and checks if the pollution is prototype is polluted. So another issue with this method is like it can't scan authenticated pages because you give millions of domains to the given the script, and so what happens is like you can't provide credentials of each and every website, right? So that's the issue with this Python selenium script. So to solve this issue, what we did was like we created a Chrome extension, which you can think of it is like an exact port of the Python script, but in the Chrome. So it does same as the this Python selenium script, but in the Chrome. So you can casually surf each and every website, and if there is a vulnerable location parser, it finds. So this thing has disadvantage. Like you can guess it. Like it is not scalable like the Python selenium script. You just throw the millions of domains list, and it will scan. For this, you have to manually surf each and every website, right? So that's the disadvantage. As I said, it has similar disadvantage like the Selenium script. It can only find vulnerable location parsers. I mean, the query parameters are the hash parameters of JavaScript. So to solve this, so as I said, it just sprays the payload and hopes for the pollution to occur. So we need a proper tool, like a tool which can do program analysis, like static analysis tool. So that's where I used CodeQL, which is a SEML's static analysis tool. It's now acquired by GitHub. So basically, it's a cool tool. Like you can model your queries according to your need, and basically you have to model each and every instance of prototype pollution in the application, and create the database and run the query on a given application. So basically you have to download all the JS files of the application. So it's hard to scale this up, this method too. But the main advantage is like it can find all prototype pollution in the given application. So that's it about the detection. You can maybe you can try new stuff to improve the efficiency of these methods, so that you can find new vulnerable applications in bug bounty programs. Because I really believe that there are so many websites which are still vulnerable to this issue. So basically, so once you find the prototype pollution, it's just not an impactful bug in the web application. The prototype pollution itself is not an impactful bug. So you need something like a script gadget, which can escalate the prototype pollution to cross-site scripting in the client-side application, or remote code execution in the server-side application. So you need something called a script gadget. In case of client side, script gadget is a JavaScript sync trigger, which can be triggered via a prototype pollution. So I just shared an example here. Like there is a function named hooks call. It iterates over window.hooks object, and it evaluates all the window.hooks properties. So with the for I in notation, it actually iterates over the given object, and also iterates over the iterates over its prototype chain. So it can, if it finds any properties on its prototype chain, it will also evaluate. So what happens if you can pollute a property in the middle, which means you got an cross-site scripting on the application. So this same script gadget I used in Elastic's product, which I'll show you in the next case study. So this is called a script gadget. So here hooks call is called a script gadget in case of client-side applications. So this is really an interesting part in the whole research. Like you have to spend a good amount of time finding script gadgets in the given application. It's pretty hard. Like you need to like debug whole JavaScript all the time. If you are lucky, you can find script gadget immediately using file descriptors, untrusted types, or security MB's pollute.js. If you are not lucky, you have to manually find it. So I thought of creating a CodeQL query to manually find these script gadgets, but because of because of some issues, I left in the middle. You can try this stuff. So that's it about the, like now we found the pollution on an application, we found a script gadget, we just report it to the program. So they'll give bounty and all. So there is more we can do, like you can store the vulnerable code, like you check which application, which third party, which led to the prototype pollution in the application and store it in a database and use this source code to search in like source code engine called public.www.com where you can search source code. So basically you paste the vulnerable code in that source code and it will find Alexa top 1000 websites. If you are lucky, you'll find similar websites using the same library. That's it about identifying the vulnerable library. Like you store the code in the database and you can do some passive finding, like using burp regular expression search in burp passing mode or source code search in public.www.com. Yeah, that's it about methodology part of this whole research. Like this is different stuff we did during the whole research. So now let's talk about the real bugs we found on applications. Like we found numerous bugs. I just took three out of all these bugs, and I'm going to show about them. Like this one is like at the time I'm in my BTech and I was bored of studies, and so I went to a private program like which is my favorite, and it is a pretty Java intensive program. So what I did was like I took the domains, all the subdomains of the program, and ran my Selenium script, and it didn't find anything. So what I did was like I believed that it definitely has prototype pollution because it is, as I said, it is a Java intensive application. And then what I did was like so it didn't, as I said, Selenium script didn't find anything. So I installed my Chrome extension and scanned pages on top of my mind, and it didn't find anything. So I decided to use a static analysis tool, which is CodeQL. So what I did was like I created a Python script which basically downloaded all the JS files in the application, and using this CodeQL command, you can create the database from that JavaScript. So you create a database, and then this is the query I wrote, using the references from github.com CodeQL/CodeQL. I wrote according to my need, and I scanned the on its vulnerability, and it surprisingly it found only one prototype pollution. Basically, we found this prototype pollution, and we took a week to find cross-site scripting on that application because it's a pretty hard. We were able to we took 2 days to convert the theory into prototype pollution and find a script gadget for 2 days, and finally we were able to achieve access, and we reported it, and they paid us $4K for the bug. So next case study is like this bug was found by Harsh and Rahul, which is a pretty interesting bug. So when I thought I had this idea of creating a Chrome extension to scan authenticated pages. So I created an extension, and my extension looks like this, and it reports when a prototype pollution is payload. I think at the same day, Harsh and Rahul also thinking about. I'm also collaborating with them, and at the same day, they also created an extension which reports if it finds a prototype pollution. Basically, the first website Rahul visited, which is apple.com, showed it's vulnerable to prototype pollution, and he was surprised. So he didn't believe it. He thought it's a false positive. Once he properly checked it, and it actually is an true positive, and they they found a script gadget and bypassed some WAF, and they were able to achieve prototype pollution. So basically, Apple is using a third-party library called CanJS dparam, which is vulnerable to prototype pollution. And Rahul submitted the bug. Rahul and Harsh submitted the bug to GitHub CanJS dparam. And Apple, they paid them $6,000 for the issue. Next one is, like as I said, we have a Python selenium script, right? So what it does, like it scans the given URLs, and if it finds any prototype pollution, it sends a notification to our Discord server. So one day it sent a notification which is a product of Elastic. So it sent a notification saying that it found a prototype pollution, and I immediately found a script gadget and reported it to them, and they paid us $2,500. As you can see, as I already told, hooks call script gadget. I told about. I was speaking previously, right? This is the gadget. Like you can pollute any property, it gets evaluated. So that's the script gadget. I used it here. So let's see the results. Like we found a numerous application vulnerable to prototype pollution. Like we nearly found 18 libraries which are vulnerable to prototype pollution, and we reported 80 access to bug bounty programs, and we collectively earned $40,000 with this bug. Now, Harsh will speak more about the mitigations part of this.
Good.
Thing.
Thanks, Mohan, for going into details about methodology and results of the research. So let's talk about the mitigations you can apply in your code bases to fix this vulnerability. So first of all, just remove the vulnerable code. So we have seen that there is no easy way to fix this vulnerability because there are a lot of bypasses. There are like no clear ways to fix it. So for example, if you look at, there are some common methods developers were using, like we were reporting, and they were fixing it using this methods called freezing the object.prototype. What it does, it basically freeze and you cannot add any other property. So freezing or sealing or maybe object.create null. So this way, the object won't have the prototype property altogether. So these were not enough. We were able to bypass these fixes. So if you want to go into the detail of finding way to way around this, check out our teammate Blackfence talk, Volgar CTF, and where he explained like how you can bypass this mitigations as well. He went really deep into the mitigations part of it. But yeah, at the top of my mind, I can just say remove the vulnerable code, or otherwise you can maybe use of object.has on property and check if the property you are taking is actually belong to that object or not. It will return a Boolean value, and then you can confirm using it. Now to the end of our talk, what else you can do? Like there's a lot of has been done by our team, and we are looking from other people to work on this because it's such an interesting attack surface and it's a very new attack surface. So for example, we were focusing on client-side prototype pollution for the while, but there's basically JavaScript can be run on server side, and with that it comes like this vulnerability can be exploited on server side, which basically means you can find vulnerabilities like SQLi and RC using this. So that's another great area of research. And another thing is related to browsers. So browsers are currently discussing ways to mitigate this vulnerability at browser level itself. So there's this GitHub discussion going on related to these mitigations, and people trying to come up with proper mitigations. So maybe you can go into this mitigation part of from a browser side. So yeah, that's about conclusion. Here are some amazing people who worked on this research with us, and yeah, a lot of great people. Give them a follow. They really put good stuff on the internet. So yeah, give them a follow. And these are the other researchers who were not actively contributing, but it basically comes from their own bugs. Like if you see WC Bowling, he was the first person whose bug we found on HackerOne. He reported the first prototype pollution that we spotted. So that's where we got the interest from. So these people are amazing. Just give them a follow. Yeah, thanks. And if anyone have any question related to this class or the methodology or anything, just shoot it.
Available in the
Yeah, yeah,
Yeah, yeah.
it's publicly available.
It's available on GitHub.
Yeah,
We open
it's
sourced everything. You can
yeah,
find everything.
like almost all the stuff is shown here. It's basically available via the blog or via the
So visit github.com/blackfan. You can find many resources regarding this vulnerability.
Thank you.
Yeah. So most of the script gadgets you see, you don't have to find yourself. Like all are public and people are actively contributing that to that GitHub repo. So you can find those script gadget as well, the Chrome extension as well. So most of the part of the research is already out in public. Yeah. So I think it started by this collaboration. So like I said, we spotted this HackerOne vulnerability by WC Bowling, and at the same time, I was talking with Mohan, and he has already started working on it. So we just started collaborating on this work together, and he had a broader set of researchers who are already working on this. So that's how we started. Then everyone has their unique ideas. Like he said, we were also making a Chrome extension. So we just put our all thoughts in one Discord channel, and that's how it went. So it's generally collaboration. If you are hacking, try to collaborate as much as with people, because maybe something you are making is already done by other, and they may have an idea to improve it. So generally collaboration that lead to this. Yeah, thank you all for attending our talk.